All right, good morning all of you, welcome back. I think this is the fifth lecture of this course. Last time we were looking at advanced control loops that are very commonly used in the process industry, namely ratio controllers, cascade controllers, feed forward controllers, override controllers. Continue and discuss override control and valve positioning control. Override control, well, override control like the word indicates, an overriding circumstance occurs during process operation which can potentially result in a safety hazard. So, then you have override control to ensure that the unsafe condition does not arise during process operation. And what override essentially means is the same manipulated variable is adjusted by different controllers. Okay. For a set of conditions, for example, the steam valve is moved by the level controller. If an unsafe condition develops, or the steam valve is controlled by the temperature controller. If an unsafe condition develops, then the steam valve is moved by a level controller, and so on and so forth. So, this is best explained, instead of me blabbing on and on. I think the best thing to do would be to explain it using an example. So, here is a very simple example. This is the bottom of the stripping section of a distillation column. You have got the reboiler which is taking in steam. This steam is causing vapor to boil up. Okay. Now, ordinarily what happens is the steam valve is moved by the temperature controller. This LS is actually low select. LS is actually low select. Okay. That means it takes in the signal, the output of the temperature controller, as well as this guy, which I will explain a little later. Whichever is the lower of the two, that is the signal that gets passed to the steam valve. Now, what we are doing on the other side is the level in the bottom sump of the column is controlled using the bottom's flow rate. All right. It may so happen that the level is reducing and this valve is fully closed, and yet the level still goes on reducing. Now, you would not like the level to go down below say 10%, because then the tubes will get exposed. The tubes in the reboiler must always be dipped in liquid, and no liquid inside the reboiler is an unacceptable condition, because then the reboiler or the tubes in the reboiler may get burnt. So, to prevent that, what you would like is, if the level is going down and is continually going down even as this valve has fully closed, you would like that the steam be reduced. You would like to pinch the steam valve. So, if level is decreasing and it continues to decrease, steam valve must be pinched. Steam valve should be pinch the steam valve. Okay. So, ordinarily the steam valve is being moved to hold a tray temperature constant, but should the level go below and continue to go down, you would like that the steam come under level control. So, what then you would like is that the steam valve should be pinched, so that less steam is given, and as less steam is given, there will be less boil up, and so the level will come back up. So, this is implemented here in this way. Here is the level signal, this is the level signal. You multiply this level, let us say level is 50%, you multiply it by 5, if the level is not too low, this signal will be usually greater than 100%. Okay. Now, let us say the level is going down, level goes down to, let us say 20%, 20% times 5 is 100%, exactly equal to 100%. Now, the level is further going down, what will happen is, if level goes below 20%, this signal will go below 100%. If level continues to go down, then this signal ultimately will become less than this signal, and the low select will now start sending this signal to the steam valve. So, for example, let us say temperature controller output is 50%. If the level goes below 10%, then this signal goes below 50%, and then the low select will pass this signal and this signal will not be passed, right. So, this would, if the level continues to go down below 50%, below 10%, then this signal will go below 50% and this valve will get pinched, right. So, this is an example of an override controller where the overriding circumstances are reducing level in the bottom sump of the column. If the level continues to go down, you would like that the steam valve be pinched, all right. So, this is an example of an override controller. This need not necessarily be a proportional a multiplier only, it could be a PI controller. In case it is a PI controller, note that ordinarily this would be going through, the PI controller will keep integrating whatever is coming from here, and that can cause this output to saturate beyond 100%, way beyond 100%, and this is known as the reset wind up problem. Those of you who do not know about it, I mean it is covered in reasonable detail in any of basic controls textbook. So, one has to be aware that these override controllers, by the very nature that the overriding circumstance is an exceptional circumstance which does not normally occur. Therefore, the controller, if it is a PI controller, would actually be saturated because of reset wind up, okay. And things have to be done to circumvent that problem, which we will not cover here. Another very useful control structure or controller is called the valve positioning controller, sometimes also referred to as an optimizing controller or optimizing control. What we are doing here is, and this is again best explained using an example. Ordinarily in distillation columns, what you have is the hot vapor is condensed in the condenser using cooling water, okay. So, if the pressure of the column is increasing, that means more vapor needs to be condensed. What you would do is you would increase the cooling water flow, and therefore, condensation rate would go up and the pressure will get back down. So, this is how ordinarily pressure is controlled in most industrial columns. You typically do not have a valve here, because for industrial scale systems the vapor flow rate is very large, and to accommodate that vapor flow rate the pipe would be very thick or a large diameter pipe, and to install a valve on that, I mean that would be an expensive valve. So, this is usually not the case in industrial columns, okay. By design, you would like to operate the distillation column at as low a pressure as possible. Why is that? That is because if you look at the vapor equilibrium, for example, for a binary system, if you look at the XY curve, X is the liquid phase composition, Y is the vapor phase composition in equilibrium with the liquid phase composition. You would have seen this in your textbooks so many times. This vapor liquid phase envelope, let us say, looks like this at a certain pressure. If you keep decreasing the pressure, what you would see is this phase envelope moves away from the 45-degree line. So, in other words, if the pressure is increased, the XY envelope moves towards the 45-degree line. What that essentially means is, as the pressure, operating pressure of the column is increased, the separation gets more and more difficult. What is that supposed to mean? What is that supposed to imply? That means to get the same separation, you would require more and more reflux, okay. More and more reflux implies you would be consuming more and more steam, all right. Therefore, per kg product your steam consumption would go up. So, what is desirable then is that your column be operated at as low a pressure as possible, okay. So, I would like to operate the column at minimum possible pressure, okay. Now, there is a set point, this should be VPC, valve positioning controller, okay. Now, to understand what the valve positioning controller is doing, consider the following. Let us say my valve is, my cooling valve is 50% open. What that essentially means is, if I start putting in more cooling water, condensation of vapor will go up because I have got colder tubes in the condenser. Now, because condensation rate will go up, what that means is the operating pressure of the column would go down, right. So, I am initially at steady state, my valve, cooling water valve is say 50% open. To reduce the operating pressure of the column in order to minimize steam consumption, what I would like is that the cooling water valve be opened. In other words, what I would like is that my column be operated all the time at nearly fully open cooling water valve, because a nearly open cooling water valve implies the column is operating at as low a pressure as possible. I hope this is clear. What I am saying is, I would like to operate the column at nearly fully open cooling water valve, because this is what implies that I am operating the column at as low a pressure as possible. Okay. All right. How is it then done? You measure the valve, the output of the pressure controller, which is the valve position. Okay. You measure, you have this valve position, you compare it with the set point, since you want the valve position to be nearly fully open. Let us say the set point is 95%. Now, what happens is, this valve position controller decreases the set point of the pressure controller. So, this was initially 50% open. Since it is not at 95% and I need to open this valve further, the valve position controller decreases the set point. So, what that essentially means is, compared to the set point now, my column is at a higher pressure. In order to bring the column at the set point pressure, as at the desired pressure, this pressure controller would increase the cooling water flow, because I want to increase condensation to reduce the pressure. Okay. So, as the set point of this pressure controller is decreased, pressure controller will open this valve, and slowly but surely what was 50% open would slowly but surely approach the set point, which is, so this will go to 95% through the action of the valve positioning controller. What the valve positioning controller is essentially doing is, it is saying that okay, my valve is, cooling water valve is not fully open, that means I can reduce the pressure of the column. So, when I reduce the pressure of the column, the pressure controller opens the cooling water valve, and so slowly but surely my cooling water valve approaches nearly fully open condition, and once it approaches that condition, what I have is my column is operating at as low a pressure as possible, which is what I desire. All right. So, this is an example of a valve positioning controller. This is also sometimes referred to as floating pressure control. Floating pressure control. Okay. Maybe I should give you another example of valve positioning controller. For example, consider, let us say I have got a big pump, and let us say it is a variable speed pump. Okay. That means its rotational speed is adjustable. This is indicated by this valve, and this pump is actually feeding n number of downstream units in parallel. Okay. Okay, so, you are feeding whatever you wish to feed to process number 1, process number 2, process number n. All right. Every process requires a certain amount of feed, and that is ensured by having a flow controller, and each of these flow controllers has a set point, which is the desired feed rate to the process. Okay. Note that I want to operate my, whatever is the demand for process 1, that is the set point for this flow controller, whatever is the demand for process 2, that is the set point for this flow controller, whatever is the demand for process n, that is the set point for this flow controller. All right. Now, whatever is desired by each of those processes, that must be given. Okay. This pump, since it is a big pump, consumes a lot of electricity, and electricity is expensive. Okay. So, what I would like to do is, while meeting the demand of all the processes, I would like to minimize the RPM at which this pump is rotating while meeting the demand, while meeting the process demand. Okay. So, I want to minimize electricity consumption, pump, I want to minimize pump electricity consumption, and the way to do it is, you would like, this is equivalent to operating the pump at the minimum possible RPM, rotations per minute. Okay. Now, how do I decide whether the RPM is minimum or not? Well, to decide that, let us say the most open valve right now, pump is operating at a certain RPM, there are certain flow set points which are for process 1, process 2, process n, and the most open valve, see, each of these valves will have a certain opening. Let us say the most open valve is 50% open, most open valve is 50% open, MOV, most open valve is 50% open, the other valves are less than 50% open, let us say 20%, 30%. Okay. Now, what that means is, I am unnecessarily pinching this most open valve, unnecessary pressure drop is being taken across the valve, and what that implies is that I am generating too much pressure by rotating the pump at a high RPM. So, if the most open valve is only 50% open, what that means is I can reduce this RPM. If I reduce this RPM, pressure here would decrease, flow across the valve would decrease, and in order to maintain the flow that is demanded by the process, the flow controller would open the valve. Okay. So, till when can I continue to decrease this valve? Well, to reduce the RPM till the most open valve becomes nearly fully open. So, this minimum electricity consumption, which is realized by minimizing the RPM of the pump, is equivalent to saying that I would like the most open valve to be nearly fully open. Okay. How do we realize that? Well, I have got my valve positions here. If I send it to a high select, which will select, the output of this high select is the most open valve. I send this to a valve positioning controller. Okay. The set point of this valve positioning controller is, let us say, 90% or 80%. Okay. This is the set point. If this most open valve is only 50% open, valve positioning controller will reduce the RPM. As the RPM is reduced, in order to maintain the flow, the flow controller will open the valve, right, and this opening will continue till the most open valve, MOV, till the most open valve is almost 90% open. Okay. So, this is another example of application of valve positioning controller, and it is for this reason that valve positioning control is also sometimes referred to as optimizing control. Optimizing control. All right. That is, by implementing valve positioning controllers, what you are trying to do is either minimize steam consumption, minimize electricity consumption. Another place that I know it is used is to maximize production or maximize throughput. Optimizing controllers are also used in that application. We will talk about that through the course, but the point is valve positioning control is routinely employed in order to make your operation as economical as possible. Okay. By the way, getting back to, since this is there, I should highlight this. You see, the pressure, when you have this kind of a system in place, the pressure of the column will float, all right. So, days are hotter. So, since the days are hotter, therefore, the minimum achievable operating pressure would be actually higher. Nights are colder, energy is anyway getting, you are losing more heat, the column is losing more heat, probably at night, since the nights are cooler, the operating pressure of the column would be slightly lower, right. So, if you look at the diurnal cycle, you will see that the set point of this pressure follows the diurnal cycle. In the days, pressure increases, at nights pressure decreases. Now, since the pressure is floating, note that if you take a binary mixture, an AB binary mixture, let us say, for a given P, for a given pressure, if you specify composition of one of the components, the other mole fraction would be 1 minus that. So, if you specify, let us say X A, and if you do a bubble point calculation, the temperature at which the mixture boils, let us say a 30% A mixture boils at a pressure of 1 atmosphere, is uniquely determined, it is a unique number. So, what is done, because temperature measurements are much more robust than composition measurements, what you essentially do is, in order to hold the separation, instead of directly controlling compositions, what is typically done is, you hold the tray temperature of a certain tray inside the column constant by manipulating either the reboiler duty or manipulating the reflux or both, and these situations will. But the point is, if the pressure itself is changing, the temperature at which if the pressure changes, the temperature at which you will get X A composition will also change. So, in floating pressure control, if you are implementing temperature controllers, then you will have to have pressure compensated temperature set points. And just to make the point, just to clarify it further, what I am essentially saying is, if the column is operating at 1 atmosphere or slightly above atmospheric pressure, let us say the temperature set point that gives you the right kind of separation is 125 degrees Celsius. Okay. Now, if the operating pressure of the column goes up because of the action of the valve positioning controller, then for the same separation at the higher pressure, same composition liquid will boil at a higher temperature, therefore, the temperature should be higher. So, if pressure goes up, temperature set point should also go up. By how much? Well, that depends on what kind of a mixture you are separating, and we will cover this later, but please be aware, in order to realize energy savings, if you are implementing temperature control on the column, well, the temperature set point of the temperature controller will have to be adjusted depending on what the current pressure of the column is. Okay. Another thing that I would like to highlight is that this pressure controller is fast. It is tuned to be for a fast and snappy response. This optimizing controller, this valve positioning controller, would be a very slow, this would be tuned for a slow response. What that essentially means is, you do not want to change the pressure set point too quickly, all right. You change the pressure set point slowly but surely, and the action of the pressure controller will cause the cooling water valve to open. Okay. since it is supposed to be a slow controller, many a times these valve positioning controllers are I only, integral action only, just a slow integrator. Okay. Another thing, why is this not 100%? I could have given a set point of 100%. Well, if I give a set point of 100%, then because of local disturbances, should the pressure of the column increase, this valve is already 100% open. I lose pressure control because I cannot increase the cooling duty anymore because the valve is already 100% open. So, to reject pressure, to reject disturbances that cause pressure surges, small pressure surges, I still need this set point cannot be 100%. I will still need some slack, so that should the pressure increase, I am able to do what? I am able to, this pressure controller can still increase the cooling water duty to take care of local disturbances. So, this back off or this trim in the set point will always be there. This will never be 100%, it will be less than 100%. How less? That depends on the system, that depends on how big the pressure surge is, for example, over here. I think that takes care of all the advanced control systems that we have. Last but not least, well, this is not the end. We are going to take a look at multivariable systems. Well, if you look at any reasonable simple chemical process, even if you look at a distillation column, if you look at a reactor, just to motivate the problem, let me give you a few examples. Let us say I have got a CSTR. Okay. Reactants are flowing in, and just to show that it is a CSTR, products and reactant mixture is flowing out. Reaction is exothermic, so I have got some cooling circuit there, and which is indicated, let us say it is a jacketed CSTR and the heat is removed by circulating some cooling water. Okay. And let us say I am controlling the temperature by adjusting the cooling water flow rate, okay, and level, let us say, is being controlled by adjusting the flow out. Let us say this is under flow control. If the set point of this flow is increased or decreased, that means if the flow rate of this guy changes, do you think the temperature of the reactor will remain where it remains, or do you think it will get disturbed? The temperature will deviate. Obviously, let us say the feed is cold, you are putting in more cold feed, right. This cold feed, when it mixes with the reactor reaction mixture in the reactor, it will cause the temperature to go down. As the temperature goes down, this temperature controller will adjust the cooling water flow rate to bring it wherever it needs to be brought, all right. The point is, whatever you do in this loop affects this loop, okay. This is what we mean by a multivariable, what I do here affects not only this, but that and that also, okay. This is what is referred to as a multivariable control system. And just to explain this further, a single input single output control, how does a single input single output control system look? Here is my process. This is the output from the process. I take it back, this is the set point for y, let me call it y1, this is y1 set point plus minus, this goes to a controller, let us say it is a PI controller, process 1, which adjusts an input, all right. Well, this is a single input single output system. What would be a multivariable system? I also have a process 2, okay. I have an output 2 which is being controlled by adjusting input 2, and I have a PI controller, let us say, that does that. So, this is shown here. So, I have got y 2 set point, I have got PI controller number 2 which is adjusting u 2. Okay. Now, even if the controller is not there, if I move input 1, y 1 will get affected, cause and effect relationship. However, y 2 also gets affected. How do you account for that effect? Well, essentially what you are saying is, and I will put something in there. When I move input 1, not only is y 1 affected, y 2 is also affected. Similarly, when I move, if I do not look at the controllers, I just look at u 2, if I move u 2, not only does y 2 get affected, y 1 also gets affected. All right, and whatever I put in these blocks marked question mark, well, that represents the interaction. These question mark blocks actually represent interaction between the two loops. So, this is actually a multivariable system where I do something here, it affects this as well as that. I do something there, it affects that as well as this. All right. So, this is in short a multivariable system, and there is interaction between the inputs and the outputs. Everything is not diagonal, so to speak. Here is without the controllers, what we have is u 1 affects y 1 through this transfer function g 1 1, and the way to interpret these subscripts is, the first subscript is, if I say g I j, if I say g I j, I refers to the output, y refers to the input. This is the nomenclature, or this is how matrix algebra is defined as. So, when I say g 1 1, this g 1 1 is to be interpreted as effect on output 1 of input 1. If I look at g 2 1, what is this? This is effect on output 2 of input 1. You can see this effect on y 2 of u 1. So, that is referred to as g 2 1. Similarly, g 1 2 is effect on output 1 of input 2, that is effect on y 1 of u 2. Okay. You can see that these two g 2 1 and g 1 2, these are the interaction terms. I mean, looking at it slightly mathematically, what we are essentially saying is, y 1 is equal to g 1 1 u 1 plus g 1 2 u 2, y 2 is g on 2 of 1 of u 1 plus g on 2 of 2 u 2. Okay. When these two, this is the input output relationship. You can see that y 1 is affected not only by u 1, but also by u 2. Okay. Similarly, y 2 is affected not only by u 1, y 2 is affected not only by u 2, but also by u 1. All right. So, when we write these two equations in matrix form, this is what we get in matrix form. These are the same two equations written as in matrix form. So, what we are essentially saying is y vector is equal to let us call this GP, a matrix GP times U. Okay. And even though we have shown only a 2 by 2 system here, we can have a more complex system. It could be 3 by 3, 4 by 3, it need not necessarily be square, it could be non-square, and so on and so forth. Okay. The most general representation would be in this matrix form. All right. So, we have just looked at the matrix description of a multivariable process, simplest of them being a 2 by 2 system, 2 inputs, 2 outputs. Now, so this is my multivariable 2 by 2 process, and what I am now doing is controlling output 1 using input 1 and controlling output 2 using input 2. All right. What we then have is this is actually called a decentralized control system, and to understand this a little better, let me just say that what we have is y is equal to GP matrix times U, U being the input, vector input. Now, this input is error times a controller. Okay. So, U is equal to a control matrix times error, and error is actually y set point minus y measured. This is my controller matrix, or rather a multivariable controller. Okay. If I substitute this over in the first equation, what I have is output is equal to GP times GC, both being matrices, times y set point minus y. Okay. Now, if I collect the terms of y on one side and everything else on the other side, what I get is identity matrix plus GP GC times y is equal to GP GC, okay, yeah, G times y set point. So, what I had was y is equal to GP times U, and I set U is equal to a controller matrix times the error, which is equal to controller matrix times definition of error is y set point minus y. I substitute it there. What I get is I plus GP GC is equal to times y is equal to GP GC times y set point. Okay. And what that essentially means is y is equal to I plus GP GC inverse times GP GC times y set point. Okay. By analogy, if you remember your single input single output system, what you had there was the transfer function G closed loop is equal to, for a SISO system, single input single output system, what you had was G closed loop, that is equal to y divided by y set point, it used to turn out to GPGC over 1 plus GPGC, right, and this used to be, we used to refer to this as the servo transfer function for a single input single output system, SISO system. Well, for a multivariable system you have something similar, in the sense that you got GPGC, and since you cannot, there is nothing like a denominator in multivariable system, what you have is the inverse of a matrix. I plus GPGC is equivalent to 1 by is nothing but the inverse of 1 plus GPGC. Okay. Notice that for this multivariable system, the order of multiplication, it has to be GPGC and not GCGP, because in matrix, for scalars A times B is equal to B times A, but in matrices, matrix A multiplied by matrix B is not necessarily equal to matrix B multiplied by matrix A. So, you have to take care of the ordering of the matrices, but this is essentially the equation that describes how the output changes. This is the servo multivariable equation. Okay. Now, the simplest GC, simplest form of the controller matrix, simplest form of the multivariable controller. What is the simplest matrix that you can think of? Simplest matrix is a diagonal matrix and nothing else here. Okay. Well, this simplest, a purely diagonal what that essentially means is, when I have a purely diagonal controller, what that means is U1 U2 is equal to some diagonal term here, let me call it GC1, nothing here, GC2 times error in 1, error in 2. Okay. This is my control equation. Now, what is happening here is how the amount I move U1 based only on E1. I mean, what this equation essentially is saying is U1 is equal to GC1 E1 and U2 is equal to plus 0 times E2 and U2 is equal to 0 times E1 plus GC2 times E2. What this equation essentially is saying is the movement in input 1 is governed only by E1 and the movement in U2 is governed only by E2. That means, I do not care what is happening to the other variable, I make changes here based only on this and I make changes there based only on that. Okay. This is essentially what is a decentralized controller, which was shown to you and I am going to show it to you again. So, U1 is changed based totally on E1, U1 depends only on E1, U2 depends only on E2. All right. So, this is a multivariable decentralized control system, and while what is done to U2 is to bring Y2 back to set point, whatever I do to U2 disturbs Y1. Because Y1 gets disturbed, my controller causes U1 to change so that Y1 gets brought back to its set point. Whatever I do to U1 affects Y2, okay, and because now Y2 has been disturbed by U1, my second controller adjusts U2 to bring Y2 back, and this adjustment in U2 causes further adjustment in U1 and so on and so forth. What you see here, what has been drawn in this lousily drawn in with the black pen, is that interaction, these interaction terms, if they are non-zero, okay, if these interaction terms are non-zero, there is an additional feedback loop. There is an additional feedback loop that gets formed because of these interaction terms. Suppose these interaction terms were not there, if these G21 or G12 or both are equal to 0, then you will see that this loop gets broken. Okay. So, interaction actually creates additional feedback, and this additional feedback destabilizes your control system, and in order, and what that essentially dictates is you will require detuning of controllers because of interaction, because of additional destabilization due to interaction, due to the interaction terms, but interaction. Okay. So, this is one thing that needs to be realized about multivariable systems, that the interaction actually dictates that, for example, if there was no interaction, if it was a seesaw system, I would tune loop 1, this is loop 1, I could tune loop 1 using Ziegler-Nichols, and I could tune loop 2 using again Ziegler-Nichols tuning. Okay. So, what I was saying was that because of interaction you get additional destabilization, because interaction causes an additional feedback circuit in your process. Okay. And this additional feedback loop actually causes further destabilization, and therefore, you would require detuning of controllers. What that means is, if I had a simple seesaw systems, y1, y1 being controlled using u1 and y2 being controlled using u2, with G21 and G12 being 0, I could tune loop 1 using Ziegler-Nichols setting using for a fast and snappy response. Similarly, I would tune loop 2 using Ziegler-Nichols settings for a fast and snappy response in y2. Okay. However, if there is interaction and I implement Zn settings in both the loops, then what happens is both the loops are very tightly tuned individually. Now, because of the interaction, what you would find is that if I implement those tunings, my whole control system would either be unstable or would continue to oscillate, or the oscillations would take a very long time to die down. This is what this feedback due to these interaction terms would do. Okay. And in order to suppress those oscillations, in order to back off from the verge of instability, what that requires is you can't use Ziegler-Nichols settings, you will have to reduce the Kc in this PI controller and the Kc in this PI controller. Okay. So, detuning becomes necessary. However, note that interaction can sometimes help in load disturbance rejection. Okay. Given that in a multivariable system, y1 cannot be controlled as tightly had it been a compared to a seesaw system. Now, because the system is multivariable, y1 will have the control of y1 will have to be slightly loose or loosened enough such that, so you will require looser tuning. Now, what happens is, now the question is, how should you detune this? This meaning detuning is necessary. How do you detune this? Detuning by how much, and by how much should you detune this controller? That is the basic question. That, well, in many situations what happens is, controlling y1 tightly may be much more important than controlling y2 tightly. Many of our situations will boil down to, okay, I need tight control of y1, as long as y2 is controlled loosely, it is okay, as long as y2 does not go out of bounds, it is all right. Okay. So, in such situations what you do is you switch off this loop is off, that means the feedback loop connection is not made. Tune this loop individually. Where you desire tight control, that loop is tuned individually with the other loop of really tight. Once this loop has been tuned, you will get a very fast and snappy response in Y1. Okay. To tune the other loop, keep this loop on and then tune this second loop. So, second loop is tuned, first loop is tuned individually, first loop is tuned individually, second loop, the less important loop where tight control is not as necessary, or as tight control is not critical or crucial. The second loop is tuned with first loop on. Okay. When I say first loop is tuned individually, that means other loop is off. If you follow this procedure for tuning, what you will find is that all of the detuning is taken in the second loop. You see what I am saying? So, all of the detuning is taken in the second loop, first loop is tightly controlled, that would give me acceptable control performance. Okay. What if both the control objectives are relatively equally important? Well, that gets slightly technical, and maybe we will cover this in the next couple of lectures. For that some amount of theory is necessary, and we will do that maybe in the next couple of lectures. With that, I think I would like to end this session here. Thank you very much.